Chemistry. This is lesson 2 from the reactions unit. This is a lesson that I accidentally skipped over, so it's going to seem kind of basic compared to where you are now, but it'll serve as a good little review for a few things, and I just wanted to squeeze it in before the end of the reactions unit. So here we go. It's just a short lesson. So chemical equations are the centerpiece of the study of chemistry. Chemical equations are a recipe that shows how reactants combine into new substances called products. So over on the left are the reactants. That's what's going in. Those are your ingredients, and what you're getting out is are the products of that reaction. The one-way arrow indicates that the reaction moves from left to right. Here are 3 ways to interpret this equation. 1 molecule of CH4 and 2 molecules of O2 combine to produce 1 molecule of CO2 and 2 molecules of H2O. Now that's at the molecular level. Unfortunately, we're not able to see molecules or weigh molecules or work with them in general. So unfortunately, this is, while it's a valid way to view this equation, it's not helpful in our actual working with chemistry. So there's a molecule of CH4, 2 molecules of O2, and by basically smashing into each other, breaking apart, and recombining, they form 1 molecule of CO2 and 2 molecules of H2O. Or we can view the equation in terms of moles. So we take that same equation, 1 mole of CH4, so a big basket of CH4 molecules equaling 6.022 times 10 to the 23rd, and 2 moles of O2 combine to produce 1 mole of CO2 and 2 moles of H2O. So just as we learned that we can measure the thickness of a piece of paper and weigh a piece of paper by taking a whole lot of pieces of paper, a bundle, a stack of paper, and knowing how many pieces are in that stack, and weighing the stack and measuring the stack and then dividing by how many pieces of paper, that will tell us the mass and the thickness of a single piece of paper. Similarly, we can learn the characteristics of individual molecules in a reaction by taking big bundles that are big enough for us to see and weigh on a scale. And those bundles are called moles, so they're simply a number of molecules or atoms. Or we can view the equation in terms of ratios. So we take the same equation. So what we say here, this is actually the most sophisticated and the best way to view it. Whatever number of moles of CH4 reacts, twice as many moles of O2 are needed. This requires a ratio of 2 moles of O2 for every 1 mole of CH4, whatever those numbers are. So if we want 1 mole of CH4, we need 2 moles of O2. If we want 2 moles of CH4 to react, we need 4 moles, twice as many moles of O2. If we want 100 moles of CH4 to react, we need 200 moles of O2. So you think of it as just a relationship that whatever number of moles of CH4 you want to react, you need twice that many moles of O2. So 1 times whatever the number of moles you need to work with are, 2 times whatever number of moles of O2 that you're going to work with, and then 1 times the number of moles. Notice the 1 in front of CO2 and 1 in front of CH4. However many moles of CH4 you react, you're going to end up with that same number of moles of CO2 because they both have a 1 in front of them. With the H2O, you have a 2 in front of the H2O just as you do in front of O2. So however many moles of O2 you use, you're going to get out that same number of moles of water, H2O, because it's a 2-to-2 relationship. That's the same as saying a 1-to-1 relationship. There's the same number of both. So we should view coefficients as ratios of reactants and products, not as a specific number of moles of each reactant and product, but as a 2-to-1 relationship, a 3-to-1, a 5-to-2, whatever happens to be the coefficients in that reaction. So particulate diagrams provide a simple picture of the motion of atoms in a chemical reaction. the way that chemical compounds break apart and recombine will be covered later in this course. So here you have one CH4 and two O2 molecules. What happens is very simply they smash apart. And it's a special study of chemistry called kinetics that deals with how does that reaction take place? What exactly smashes into what? We don't need to concern ourselves with that right now. We're just going to say that somehow some number of O2s and CH4s smash into each other in some combination that break them apart and cause them to recombine. So particulate diagrams show a beginning and a final diagram of a reaction. It might also show an intermediate state of the reactants, as you're going to see here. So we're going to smash apart the methane and the two oxygens, and there they go. Now they're broken into their individual atom components. Then once they do that, sometimes they'll go back to where they started, but we're assuming they're not going to do that here. They go forward to form CO2 and H2O, so you're going to get one molecule of CO2 and two molecules of H2O. Notice you started with the same number of oxygens as you ended up with, 4, same number of hydrogens as you ended up with, 4, and same number of carbon as you ended up with, 1. Antoine Lavoisier, known as the father of chemistry, developed the idea of conservation of mass in the 1700s. Conservation of mass means that the mass of the reactants before a chemical reaction must equal the mass of the products after the reaction. This means that if you bulldozed and burned Hoover High School to the ground, the mass of the rubble and smoke would be exactly equal to the mass of the school before it was destroyed. In other words, you took a big glass dome and you were able to put it all over Hoover High School to trap anything inside. Then when you smashed the school apart and burned it, and you captured all the smoke that came up from the fire, and you weighed it and you weighed the rubble, it would equal exactly the same weight as the original high school before you destroyed it, because there are the same number of atoms and molecules in the rubble and in the smoke that you burned as there were in the original high school. So this means that the number of atoms of each element in the products must equal the number of atoms of each element in the reactants. That's an important concept when we come to balancing chemical reactions. All right, that takes care of this lesson. It was kind of misplaced, but it gives you a little bit of review of what a mole is, how it relates to actual individual particles. And so that will conclude the reactions unit.